You know, quantum dots are these amazing little crystals that are totally changing our world, from the TV you watch to the medical labs that keep us healthy. But a lot of them are made with some pretty nasty heavy metals. So today, we're going to dive into some really cool research about a newer, greener way to make these things, and maybe even more importantly, a powerful theory that lets us design them with incredible precision.
All right, so here's the plan. First, we'll get a quick refresher on what quantum dots even are. Then, we'll get into the big problem with the old ones and why we desperately need a safer alternative. After that, we'll peek behind the curtain and see how scientists actually measure these tiny things, and then unpack the really clever theory that predicts how they should behave. And the best part? We'll see that aha moment where the theory perfectly lines up with reality. Then, we'll wrap it all up with why this is such a huge deal for future tech.
Okay, first things first, what exactly are quantum dots?
Oh, I want you to imagine a crystal so ridiculously small that you could fit thousands of them on the tip of a single human hair. They are so tiny, we're talking just a few atoms across, that they don't really have a length or a width in the way we normally think about it. Scientists call this zero-dimensional, and at that tiny scale, the really weird rules of quantum mechanics just take over, and that gives them some truly unique superpowers.
And their most famous superpower is color. It all comes down to this idea called quantum confinement. Think of it like a guitar string, right? A shorter, tighter string gives you a higher pitched note. It's the same idea here. A smaller quantum dot kind of squeezes its electrons more, which makes it spit out higher energy, bluer light. As the dot gets bigger, that squeeze gets weaker, and it emits lower energy, redder light. It's this incredible, size-based control over color that makes them so valuable.
And this isn't just science fiction in a lab somewhere. This stuff is already in our lives. Quantum dots are the secret sauce that makes modern TV screens have such jaw-droppingly vibrant colors. They're making solar panels and LEDs way more efficient, and they're even being used as tiny little beacons in medicine, helping doctors find and track diseases inside the body.
But there's a catch. There's a pretty big problem with a lot of the quantum dots being used today, and that brings us right to the heart of this research, finding a safer, greener alternative. See, the problem is, for a long time, the best quantum dots were made with stuff like cadmium selenide. And cadmium, well, it's a toxic heavy metal. It's bad for our health, it's bad for the environment, and governments are already starting to regulate it. So, this research focuses on a much safer option, zinc selenide, or ZnSe. It's way less toxic, which makes it a fantastic replacement for pretty much all of those applications.
Now, to make these safer dots even better, scientists give them a tiny protective coating. They create what's called a core shell structure. The little ZnSe crystal is the core, and it gets wrapped in a shell of another material, in this case zinc sulfide. This shell basically acts like armor. It protects the core from damage and oxidation, and it dramatically improves its stability and how brightly it can glow.
And get this, the way they're made is just as smart. Instead of using a bunch of harsh chemicals, this whole thing is a green process that happens right in water. They just prep the ingredients, gently heat them up to form those tiny ZnE cores, and then add a little something extra to grow that protective ZnS shell right on top. It's simple, it's effective, and it's way, way better for the environment.
Okay, so you've made these fancy core shell nanocrystals, but how do you know what you've actually made? How do you measure these tiny structures and figure out their properties? Let's get into it.
The main tool for the job is a technique called X-ray diffraction, or XRD. You could think of it like this. You're trying to figure out the shape of something in a totally dark room. So you start bouncing thousands of ping-pong balls off it. By studying the pattern of how those X-rays scatter off the nanocrystals, scientists can get a fingerprint that tells them the precise atomic structure.
So, what do those X-rays tell them? Well, first, they confirm that yes, they made the right stuff, the right crystal structure. But they also found a little problem. The bare cores without the shell were oxidizing, basically rusting at the nanoscale. But as soon as they added that protective ZnS shell, the oxidation stopped dead in its tracks. It was clear proof that the armor was doing its job perfectly.
Digging into the data even further, they could calculate the exact size of the cores. And they were just ridiculously small, averaging about 2.3 nanometers across. I mean, to put that into perspective, that is over 20,000 times smaller than the width of a single human hair.
But the data revealed something else, and this is a huge deal. The core was under what's called a compressive strain of negative 2.2%. What this means is that the outer shell doesn't fit perfectly. It's just a little bit too small, and it is literally squeezing the core. And this squeeze, as we're about to find out, is a critical piece of the whole puzzle.
So that detail about the strain, the squeeze, leads us perfectly into the theory. How do you build a model that can actually predict how these little nanocrystals are going to act?
So, we already know that size matters. That's the whole quantum confinement thing. But for these advanced core shell dots, that's just not the whole story. You also have to account for that squeeze from the shell. Both of these forces, the size and the squeeze, are working together to determine the quantum dot's final bandgap, which is just the fancy scientific way of describing the exact color of light it's going to emit.
You see, a simple model based only on size just isn't going to cut it here. The researchers needed a more powerful tool. So they turned to this really sophisticated model that could account for both the size and that squeeze from the shell. The theory calculates exactly how that mismatch between the core and the shell creates that strain, and, most importantly, how that strain changes the final color of the quantum dot.
And this all builds up to the most important part of any scientific research, the moment of truth. Does this beautiful, elegant theory actually hold up in the messy reality of a real experiment?
I mean, that is the ultimate test, isn't it? It's one thing to predict something on a computer, but does it actually work in the real world? Let's take a look at the numbers. And here it is. This is the big reveal. Remember that 2.3 nanometer core size they measured earlier? Well, the computer model predicted that a dot of exactly that size, with that specific squeeze, should emit light at an energy of about 3.40 electron volts. So they went to the lab and measured the actual light coming off the dots they made. The result? It was between 3.39 and 3.41 electron volts. I mean, that is a near-perfect match. The agreement is just excellent. It's not a lucky guess, it's an incredibly accurate prediction. This is the proof that the model, the one that includes both the size and that all-important squeeze, can perfectly describe how these complex little crystals really work.
So, what's the big takeaway here? Why does any of this matter outside of a science lab? Well, this is about designing the future of nanomaterials.
Okay, let's just quickly recap the whole journey. We know quantum dots can be tuned by their size. We've seen that a green, water-based method can create safer, zinc-based quantum dots. We've confirmed that a protective shell is absolutely key for their stability and performance. And, most importantly, we now have a theoretical model that can accurately predict their behavior before they're even made. This basically gives scientists a powerful new design framework for material science.
In the end, what this research gives us is a powerful new equation for the future. You combine environmentally friendly synthesis with incredibly precise theoretical models, and what you get is the ability to design brand new nanomaterials from the ground up, with predictable, tailor-made properties for whatever next-generation technology we can dream of.